Hi, this is Robert with Better Geiger Radiation Detectors, and today I want to try to make a video talking about the concept of radiation dose. And I think for beginners that can be kind of complicated and daunting, so what I'm going to try to do is give a very sort of quick overview primer kind of discussion of this topic to give you a little bit of an understanding and a feeling about what is radiation dose, so what it is, what parameters are involved, so what kind of feeds into this number to give you a dose number, how in practice you measure radiation dose and mistakes you can potentially avoid, and then some real world numbers for the units and kind of what the health effects are at different amounts of radiation and stuff like that. So again, this is going to be very, very superficial, but hopefully it'll still be a useful introduction for people. And I have some sources, some artificial sources here. I have some Fiestaware. I have a Better Geiger S2L radiation detector, and I have a low-cost Geiger counter based tube for some comparisons to show in the measurement part what these can and can't do and how they differ. And yeah, I'll try to do some demonstrations later. But to start, we'll get this out of the way, get this stuff out of the way, and start with my slides. So as usual, I'll try to do this in one take and work through my scribbles here and try to explain everything as I go. So sorry it's going to be a little messy as usual, but hopefully it'll get the point across. So you imagine you or someone is in a radiation field, right? So you have radiation, coming from all around. You have it from cosmic radiation or from the ground. There's some little bit of radioactive material in the soil you're near or whatever. A person is exposed to radiation, or if there was some kind of artificial source nearby giving out a lot, that might expose you in some certain way. So how do you get from this situation generally to radiation dose, and what does dose mean? So dose is meant to kind of encompass the idea of how this translates into health effects on your body, so that you can have different situations and they might be a little bit apples to oranges, but you boil it down to one number and you can hopefully gauge in one situation or another how much radiation dose you were exposed to in order to quantify what kind of health effects that might lead to or what risks you might be exposed to. And there are pretty much four main things in this sort of generic scenario where it will feed into some very complicated math and other things, which when you boil it all down, you get this whole body effective dose, or what we can for shorthand just call dose. And there are a lot of more complicated steps involved in this, but we're going to look at it in a simplified way and talk about some of those simplifications step by step. But one is the radiation type. So you've probably heard of alpha, beta, gamma. And for the purposes here, I'm going to just say gamma, but practically speaking, from a dose standpoint, X-ray and gamma are truly the same. And so, some people think gamma means high energy or X-ray means low energy. In reality, it has to do with what physical process produced that radiation. So we're just going to say gamma for now, but it's applicable also to X-rays. Where this radiation is hitting your body, if it's hitting overall equally or if it's all hitting in one particular area, that might cause a more or less strong health effect or health risk. Energy, so each individual bit of radiation, a particle or a wave or whatever, is coming in, and it can have more or less radiation individually. So if the same number of things are hitting you, but they have higher energy, that's going to mean more likely to cause some health effect. And I kind of skipped over it, but basically, each of these things coming in is considered ionizing radiation, which is different from, a microwave or a sound wave or infrared or something like that, which doesn't really have enough energy to break cells apart. And what makes ionizing radiation, or what we're just going to call radiation for short, is special is it has enough energy to basically break cells apart, damage DNA, damage cells, things like that. And in large enough quantities that can cause, significant health effects or increase your risk of cancer. So the energy factors into that, because more energy means more possibility to damage more cells. And then finally, how much or how many, that's pretty straightforward. Even if it's the same type of radiation, same area of the body, same energy, if there's more of it, you're going to have more of an effect. So the fourth is simply how much. And then you combine all these things very carefully through a lot of complicated steps and considerations, and you get whole body effective dose, or what we'll just call dose. So we're going to continue to try to simplify this story to help a little bit with the understanding and the practical implications. To start, we'll look at what type. So here we are in number 1 here, radiation type. The most relevant 3 that we hear about and we should keep in mind are alpha, beta, and gamma. Alpha is basically like a helium nucleus, and it's a charged particle. And what you mostly need to keep in mind for alpha is that it doesn't penetrate far. A piece of paper or something very thin will stop it. And even in air, a few feet or a couple meters is usually enough to, more than enough actually, to stop an alpha particle. So it doesn't travel very far. It doesn't penetrate much. Beta is basically an electron that's energetic and is flying around. And it takes a little more to stop it, but it still has a negative charge, so it stops pretty easily in matter. So 1 or 2 millimeters of aluminum, or maybe a few millimeters of plastic, or a quarter inch of plastic is more than enough usually to stop betas. So you can imagine they're not penetrating very deeply into your body, or traveling over very long distances in air either. And then finally we have X-ray or gamma. I'll just call gamma. And these are basically waves similar to other waves on the electromagnetic spectrum, like light, visible light, infrared, sound, microwaves, radio waves. All those things are on the electromagnetic spectrum, and they consist of individual photons, which can be thought of as little bits of radiation flying around. And so, gamma is kind of an interesting. It's a more complicated one to think about in terms of dose sometimes, because you have to really think about the energy. If it has a lot of energy, it will penetrate more deeply, and you can have a few inches or even a few feet of concrete or lead or whatever, and that will gradually stop more and more of these little bits, but they will penetrate deeply and sort of spread out and cause potentially damage to your body if that's your body. So alpha, beta, gamma are the 3 types mainly to think about when we look at this number 1 factor, radiation type. Number 2, where on the body? So I kind of already explained it, but as you can probably guess, different organs have different susceptibility to health effects. And, your lungs, for example, if you have a lot of radiation impacting your lungs, you might be at greater risk of lung cancer. Something like your hand, as you can probably guess, is less susceptible. So if you have some similar amount hitting your lungs or your hand or some other organ, depending on the organ and how much and where and so forth, it will have more or less of health risk or a dose associated. So, that is there are ways to factor that in, which we're not going to get into the details, but just keep in mind that where on your body the radiation is, impacting, so to speak, will affect this whole body effective dose. So number 3 on this list, type, where on body energy, is energy. And again, I already kind of explained it, but for one individual bit, I kind of illustrated it with a small squiggle or a large squiggle to sort of symbolically show high energy and low energy. When that hits your body, it's going to penetrate more deeply, which means it might reach, more sensitive organs, perhaps. Or if it's a low energy, it might just be more near the surface, where it's potentially less damaging to organs, depending on where in the body. So, for the same number of photons or the same number of things coming in, higher energy is generally going to be more impactful. And to give a couple examples here, and the units are keV or MeV, kilo electron volt or mega electron volt. But if you don't want to get deeper into the physics, just remember keV, MeV are energy. 1,000 keV is 1 MeV, mega kilo. So Cesium-137, for example, is a very common isotope, commonly used, artificially available radiation source. It has, I put a typo here, that should be a K. 662 keV is the gamma energy that it emits. So it emits gammas at this one particular energy, mostly. And cobalt-60 is another common one, and it emits actually 2 gamma lines, and they're about roughly 1.2 MeV, which would be 1,250 keV. That would be equivalent because of this 1,000 to 1. And you see both of these, almost interchangeably. You just have to pay attention to the unit. Something like uranium has a lot of different isotopes emitting a lot of different energies inside, so that will have a different behavior. X-rays are another example where it's usually a continuous spread of energies from 0 up to the electron energy, which is producing the X-rays. So it's, just another situation where you have all sorts of energies coming in, and that has to be sort of factored in somehow if you're trying to get from a situation to a radiation dose number. So that's type, where on the body, energy, and then how much, how many, straightforward. And if you factor all these in very carefully and you do the right math and do the right considerations, you can get a whole body effective dose for a given situation, or a dose rate if it's per unit time. So a dose is the total amount you get, and the dose rate is how much you're getting, per minute or per hour or for whatever. So you can think of that as like miles per hour would be dose rate. That's how fast you're going. And miles is how far you've traveled in total. So you can travel a fast speed for a short time and get the same distance as a slow speed for a longer time. And that's like dose rate and dose. So that is energy. And now we're going to circle a little bit around and look at how we can simplify this in practice or in common situations that you might encounter, how this picture gets a little bit simpler. As I said, alpha doesn't penetrate much. It mostly doesn't penetrate your dead layer of skin, or if you have a shirt or anything, it's not going to penetrate that. Beta's a little bit more, and if there's a lot of them, and if they're high enough energy, they might have a little bit of an impact beyond something superficial or a layer of clothing or whatever. But for the most part, unless you're doing something very specialized, you're in a very strange, abnormal situation, beta is generally neglected if you're just kind of measuring dose rate in a typical situation that a non-specialist or a non-expert might be dealing with. So generally speaking, alpha and beta, you want to basically exclude them. And the gammas and the X-rays, they can penetrate deeply. They can reach throughout your body. They're not shielded by a layer of clothing or anything like that. So generally, X-ray and gamma are what you need to pay attention to and what you need to understand how to measure correctly. And that's kind of the three types in the body. And the takeaway here is really your detector should not confuse gamma with alpha and beta, or to say it differently, it should usually just not measure alpha and beta. Those should be blocked from the sensor or somehow taken into account to where your detector is only measuring X-ray and gamma. That's one requirement for having a good dose rate measurement in ordinary circumstances. So that's the type. So we imagine for the moment we have only measuring gamma, and I'll actually do some demonstrations here, I think, where I can sort of explain what that means in practice. So I have here a strontium-90 source. This is a pure beta source, so it's only emitting beta. In here I have a better Geiger model S2L radiation detector, and you can see here in the background it's bouncing around a little bit, but it's about 0.08 or so microsieverts per hour dose rate. And if I put that beta source there, it does go up a little bit because this is not perfectly shielded from beta, but you see it doesn't really go up very much, maybe just a tiny bit. because it's simply shielding the beta, because this is meant to measure dose primarily. It's meant to measure X-ray and gamma. So it's got enough plastic and stuff around the sensor here to where those betas don't really penetrate, and so they don't cause a false overestimation of the dose rate. And to take the other example here, this has a Geiger tube inside, and it's quite sensitive to beta. And we'll get into the energy question as well, but for now we can see, you hear, I don't know if it goes through the audio, but you hear a count here and there, and there's a dose rate here of 0.04, or it hasn't quite settled, but 0.0 something microsieverts per hour. So not super far off from here. And when I put the beta source there, it correctly shows still a quite low dose rate, because it's not a penetrating radiation type, and it should mostly be neglected. So the risk is, if you have something that's emitting a lot of beta and you use a typical low-cost Geiger tube detector, you'll see the count rate goes up and the dose rate goes up quite a lot. So here you have about 20 microsieverts per hour, and they were both measuring around, let's say, 0.1 or so in the background. That means this was overestimating the dose rate by a factor of 200. So that's why this is people should be cautious when using typical Geiger tubes. And then looking at this number, it'll give you the number, but the user is supposed to know that they shouldn't be picking up betas when they're doing this kind of measurement. So that's really the first key point. And another situation where the same kind of issue comes into play, this is measuring a little bit of gamma, but mostly beta. And this is picking up some of those gammas, and the dose rate's gone up a little bit, so it's maybe doubled or so. And if we look at the count rate, it's around 5,000. If we go back to dose rate, you see it's about 0.2. If I take this away, the count rate will drop to, I don't know, maybe half of that. So generally speaking, it goes up a little bit because there are some X-ray and gamma coming off of this. But if we do the same thing with the typical low-cost Geiger tube, you'll see again the dose rate shoots up to 20, 23, 24 microsieverts per hour, whereas here was at about 0.2. So we're overestimating by 100 times or 150 times or so. So if you have this, this is a piece of Fiestaware. It has a little bit of uranium in the glaze. It's an antique item that people like to collect and use as a test source. It's fine for saying, okay, this is a radioactive thing, this has uranium in it. But if you look at this number and think, oh wow, this is the dose rate, I'm getting such and such dose, that will be grossly overestimated, because this device is not correctly blocking the betas or somehow in another way taking it into account, that's not shouldn't be added to the dose rate in the same way. So that is basically an impression of dose rate and only measuring X-ray and gamma. So we can now look at point number 2, which is where on the body. So we talked about radiation type. Basically, you want to measure X-ray, gamma only. We're going to say where on the body and how we can simplify that story. As I said, different parts of the body have different susceptibility. But in most situations, what the device is doing is thinking to itself, someone is holding me somewhere, and that position, wherever that is roughly equal to what the whole body is being exposed to. So that's basically when it shows a dose number here. I'll go back around to dose. When it gives a dose number, this device is saying whatever it's measuring at this location, it assumes that everywhere is the same. So that is, going from a point measurement to a whole body measurement, because this device just can't know if this is a complicated field or if it's more here or there or whatever. And that's important to consider, because the situation where this can really cause problems for people is if you have some kind of source, whatever it is, and this is a cesium-137 gamma source. If I put that on there just like that, the dose rate is going to go up to whatever it goes to. But this device is thinking your whole body is being exposed to that same level as being very close to it. So it's kind of as if your whole body were right next to that source, just, a centimeter away. In reality, you know, the source is wherever it is, and I'm holding it here. My hand is here, my arm is over here, my torso is a little bit further away. So most of my body is far away. It's not all in that very close, very high rate. And as you move away, the levels get lower. So I actually have a whole video on this called the inverse square law, about the topic of the inverse square law. So you can check that other video out if you want to get more in depth in this. But basically, if you want to measure dose, you don't want to be right up on a source. You want to have some distance, a couple feet or so is usually okay. If you're just measuring in sort of a room in some kind of elevated area where it's not a specific thing, then you don't have to worry about this so much, because wherever you're measuring is probably roughly uniform and your body is roughly exposed to whatever this is seeing, the sensor is seeing. But just be careful about going right up on something and taking a number like this and taking it at face value, because that's going to not really represent a whole body effective dose. That's just kind of some sort of arbitrary measurement here that is not really one-to-one corresponding to health effects in a straightforward way. So that's number 2, wear on the body. And like I said, the way you simplify that is don't get right on something. Radiation type we talked about, wear on the body. Now we're going to talk about energy. So another key difference between the better Geiger and most scintillators and some other types is that they're energy compensated. And what that means is that the sensor basically can see what kind of energy is coming in of the gammas, and if it's a higher energy or a lower energy, it takes that into account automatically when giving this dose rate. This Geiger tube cannot do that. So it has a tube here. All it is doing is counting. So if it gets a low energy or a high energy, it'll pick it up and it'll say, well, we got to count. And these are typically calibrated to cesium-137. So if you measure with cesium-137, it's going to be pretty accurate. But if you have a different energy, it will generally not be. So mainly this comes into play because this is a pretty high energy, and most realistic scenarios are lower, tend to be on the lower side. So what I have here is a cobalt-57 source, which is lower energy and has an energy of 122 keV, mainly as what it emits in terms of gamma. So we can put that basically in place and put our 2 detectors with the sensors right near it. And it's not a perfect setup, but just to get a rough idea, we can see basically here the Geiger tube, which is not energy compensated, is going up to about 80 microsieverts per hour, while the better Geiger S2L is energy compensated. So it knows that these gammas coming in are lower energy than cesium, whereas this tube thinks everything is 662 keV because it's not able to distinguish one energy from another, and this scintillator can. So it's showing about 13 microsieverts per hour, while the Geiger tube is showing about 80. So yeah, we have about a factor of 5 or so, and it's not a perfect test because they're both very close and it's sensitive to the position and whatever, but it's just to illustrate roughly that if you don't have energy compensation, you really can have a very dramatically incorrect dose reading. So that's another key point to keep in mind, is if you want to measure dose, basically measure something, use something that is energy compensated. And it's not that every single Geiger tube is incapable of this. There are some energy compensated Geiger tubes, but they're much more expensive and they're pretty rarely seen, or maybe never seen, in sort of hobbyist or consumer grade devices, whereas scintillators are available. That's the energy example I wanted to show. And so to basically summarize here, we talked about radiation comes in. We mainly want to measure X-ray or gamma. We want the measurement position to be representative of the whole body and not be sort of a contact measurement where the position is giving something misleading about what the whole body is exposed to. You want to make sure you have an energy compensated detector that automatically factors in X-ray and gamma energy. And then that fourth step is, that's what the detector does. It's basically counting and measuring. So you don't really have to do anything with number 4, but these 4 things combined gives you some kind of whole body effective dose. Now I'm going to talk about a couple more details related to that. And one of those is acute versus chronic. So we have these numbers, and I didn't really talk about the units, but REM and sievert are the whole body effective dose, or the dose units that we're going to be paying attention to. So most modern devices are giving you a dose rate or a dose in REM or sievert, and 100 REM is equal to 1 sievert. That's just a ratio. So it's kind of hard to keep track of these because different ones are used in different situations. REM is more often used in the US, sievert in the rest of the world. And then you have milli and micro or even nano. So milli is 1/1000th. You can have a milli REM, 1/1000th of a REM. You can have a micro REM. You can have a micro sievert, and micro is 1/1,000,000th. There's no really simple fast way to kind of keep these all in your head. You just have to pay attention to the units, and if it has an M or a micro symbol before it. One useful thing to keep in mind is 10 microsieverts is 1 millirem. That's a useful one because often they'll show microsieverts or millirem if you're dealing with kind of everyday rates and not super extremely high rates. So those are the two units. I'm going to stick with microsieverts mostly for the time being. That's what the better Geiger S2 and the S2L show. And that's what I'll stick with just for the sake of being consistent. And yeah, so acute is basically all at once, or more or less at once, not in an instant necessarily, but in a very short period of time. And what's a short period of time? Well, usually, minutes to hours, maybe a day or two. So if you get a bunch of radiation dose in that kind of time frame, it would be usually considered an acute dose. And chronic would mean spread out over a long period of time. So if you're some kind of worker employed in a situation where you're exposed to radiation as part of your job, and that's monitored by a dosimeter or by detectors or whatever, that might be spread out over a longer period of time. And you shouldn't really get a lot at one time or over the course of the year. But in general, if you're in let's say a particular region which has a higher background radiation, that would be considered kind of spread out, kind of a chronic dose. Might be a slight elevation, where if that slight elevation of rate were if you took this total dose over the whole year and got it all at one time, that might be something a little bit different to consider. But generally, if the dose rate is spread out over time, your body is less likely to experience any sort of acute effects, or getting nausea, vomiting, headaches, that kind of thing, that really happens at extremely high radiation levels at a very short period of time. And I've got kind of an analogy here. This is a gallon of water, or yeah, it's a gallon of water, but let's pretend that it's a gallon of vodka, right? Alcohol, ethanol. If someone drank this whole thing in 1 hour or 1 day, they're going to have a very bad day, and they might almost definitely will be sick and will potentially die. So think of getting a whole bunch of radiation in one go in a short amount of time. That would be like an acute exposure. Whereas if you had one spoonful of this every day for a year, that would be the same total amount of water, which is our pretend vodka here. So if you had one spoonful of this every day for 365 days, that would add up to this whole gallon. But if you're, a healthy adult, that would most likely not really pose much of a health risk to you. And that's very similar with radiation. If you get a little bit over a long period of time, your body is much more able to handle it and much less likely to experience some kind of effects. Even if it's a pretty large amount, if it's spread out over a large time, your chances of not suffering consequences from that are much better. And that's a very simplified view. It's a very complicated topic. And again, I'm not getting into details. This is just giving an impression of some key points. But acute versus chronic is something to keep in mind. And to give a little bit of a feeling for what these numbers actually mean, I'll give some examples. So a chest x-ray, you're going to get roughly 15 microsieverts in dose in that short period of time. And so that would be a small acute dose, and it wouldn't really be a significant concern, but it is something. It's a lot more than you get on a normal day. And I forgot to write it down, but if you're measuring dose rate in just an ordinary place, I happen to be in an area where there's a little bit higher than usual, or let's say higher than average background radiation. And in this room I'm in right now, I have some artificial test sources nearby and things like that. So it's basically it's a little bit elevated. But if I didn't have anything nearby, if I had sort of an empty room here, it would be closer to zero point 0.05 or zero point 0.1 microsieverts per hour. And if I were to go outside a little bit further away from some of the soil in the dirt that's in the foundation here, it would be a little bit lower still. So, but roughly 0.05 is kind of normal. It might be 0.02, 0.03, a little bit higher, a little bit lower. It varies quite a lot, but that's kind of a rough amount. So if you think about zero point 0.1 microsieverts per hour, that means in 24 hours you get about 2.4 microsieverts, right? That's that dose rate and the total dose. So over the day you would get that amount if you got a certain rate over that time. You just multiply the rate times the time. And of course, this is functioning as a dosimeter. So the better Geiger can also give you, since it's been powered on, how many minutes have elapsed, what's the average count rate, what's the average dose rate, and the total dose. So you don't have to do that in your head necessarily. You can just let this run and see after an hour or a day or whatever what the total is. But anyway, to get back to the examples, so a chest x-ray would be something like 15, and that example I gave there of a fairly high background rate would be like 2.4 in a day. So it's quite a bit higher than background, but it's still not something really, significantly hazardous. There is the ALARA principle, ALARA, as low as reasonably achievable. So, the guidelines are basically you should always reduce the dose you're exposed to as much as reasonably possible. But practically speaking, this is not a very high risk. A chest CT, computed tomography, which is basically like a bunch of x-rays from different directions, all one after the other, you would get something in the ballpark of 10,000 microsieverts. So quite a bit more here, but in a given situation, if someone, if a medical professional says you need a chest CT and we think it's worth it, then it's probably worth it to get that information, which might help you with diagnosis or whatever. And then you'll get about 10,000 microsieverts roughly. This is very, very rough numbers. And also, that would be equivalent to 10 millisieverts. And people have different susceptibilities. I'll get to that in a second. But so an annual limit for workers is it's 50,000 microsieverts. There's a little more to that, but that's kind of like a annual limit, which would be 50 millisieverts. So, that's just to give you a rough idea of where this falls into those guidelines. It doesn't mean that this is something you should get, or it's doesn't matter, or that this is a magical number, but that gives you a rough idea of, if they believe that workers can sort of safely get that amount in a year, then it's probably not a real major concern. And this also gets into other topics which are beyond the scope of this video, like, the linear no threshold model and other things which maybe are worth exploring in another video, but just trying to get rough impressions and feelings here. So if you were to get 1 million microsieverts, or 1 sievert, which would be like 100 chest CTs in a row, now you're at the level where you're at risk of acute radiation sickness or acute radiation syndrome, where you have this acute dose in a very short amount of time. And this is, again, not a hard number, but, roughly in this region, 0.5 or 2 or something, it's very personal. It's going to depend a lot on the individual, how healthy they are, how susceptible to radiation they are. Maybe there's luck involved. So when you get into this number of zeros, though, you're starting to be at a level where you might really become sick and even have a chance of death or increased long-term risk of cancer, which the long-term risk of cancer can happen, well below this. But, you're in really a serious dose if you're exposed to 1 sievert, and that would only happen in really, really extreme sort of situations like a major accident or a nuclear blast, post-nuclear blast, fallout scenario or something like that. And then if you get into 5 to 10 or so sieverts, you're really in a regime where your chance of death becomes very significant. We're roughly at the LD50, or the chance, the acute dose where 50% of people will die. And it's, again, think about the water thing. Everyone is going to be different. There's a lot of randomness to how each individual responds. This might be, this much alcohol could maybe kill one person but not another, or if it's spread out over a day or 2 days or 3 days, then one person might survive or not. So it's a very fuzzy thing, but these are just kind of rough numbers to get a sense of where the ranges roughly are. So yeah, these are some examples, and yeah, that might be a topic for more in depth another video, but that's not what this video is for. I think that's mostly what I wanted to cover. We talked about radiation type, where it's reaching the body, the energy, and how much of that radiation is there. You put that together, you get a whole body effective dose. Make sure you have a detector which is designed to measure dose and is not just something cheap, very low quality. And yeah, that's my video. Thanks for watching. I hope it was helpful. Please give some feedback in the comments if this is the kind of content that is helpful to you, if you're interested in more of this. I do plan some more videos, and check out bettergeiger.com if you want to buy this detector, or there's a couple other variations available now. This is the one I design and make and sell. And again, if you like this, like and subscribe and do those things that help this video reach other people, because the more this reaches people, the more I am likely to make more, and more motivated I am to make more content like this. So if you want to get more content like this, do those things the algorithm likes, and so forth. And yeah, you can always reach me via the website. Send something to the contact form. I can answer questions and things like that. So thanks again for watching. And yeah, that's radiation dose, quick and dirty in a nutshell.